Let me introduce Daniel Schroeder, from Sintef. So I don't know you from too long. I think I met you first time in Oslo.
Yeah.
No? It was a workshop on neuro-symbolic AI, where we presented our graph massifizer project, right? That applies symbolism to represent extreme data in the form of knowledge graphs based on semantic representation and ontology description of data. And on top, we apply geometric artificial intelligence techniques, at the neural level to support massive graph high-order pipeline architectures. So you are part of the Inceptor tool of the project, that deals with the creation of the graphs and also supports the inferences, of the using the AI technologies. So I'm happy to give you now the floor to introduce your work.
Yeah.
Thank you.
Thank you very much, Radu, and everybody welcome to my talk about enabling operator-agnostic complex processing of massive graphs through higher order pipeline architectures. It sounds a bit complicated, but like what I mainly do is I would try to relate that a little bit to what we're doing in Graph Massifizer. So there will be an introduction, like just general about graphs and graph processing, coming to graph processing pipelines and more complex graph processing. And then I will introduce concepts we use in Graph Massifizer to then on top introduce the library we have built, and at the very end try to give a picture of what we could potentially do and where maybe it's not enough time in the Graph Massifizer project for, okay? So let me start with a very brief introduction into networks at all. So like networks are omnipresent and part of our everyday lives, right? And they come in different forms and structures. So like down here, there's something like a public transport network, right? Which is structurally very different from something like connectivity networks that is underlying some of these social networks. This is from work I've done during my PhD, in which we actually built these interaction networks that underlie Twitter interactions from billions and billions of tweets with actually millions of users. And we tried to visualize it, so that was a result. Took a while to do so, but there's also molecular networks, there are family trees, and I think this is a visualization of the internet. The nodes were servers and the connections were connections in between. So message is that graphs are omnipresent and we have them everywhere, right? But it's not only that they're omnipresent, but they also became bigger and more complex to process, right? So like this example here had a couple of million nodes, and it was actually a multi-layered graph, or even a multi-layered temporal graph. You can imagine that each interaction between a pair of Twitter users actually has a timestamp. So you could bundle interactions within a time frame of like a day, a week, or something like that, and have these networks in layers. Plus, there are multiple actual layers, like the URLs people share, the friendship, things like that. So that turned out to be multiple billion edges, which we somehow had to perform community detection on and to perform machine learning on, right? And that only worked on special infrastructure and a very, very large computer. Graphs come in different forms and shapes. So there are like simple graphs, multi-graphs that can connect nodes with multiple edges. We have hypergraphs in which one edge can connect multiple nodes. They are directed or indirected. They can be mixed. They can have vertex attributes or no vertex attributes, and the same is true for edges. They can even be hierarchical graphs in which you have a graph in each of these vertices as well. And obviously they can have special properties. They can be complete, bipeptides, they can be trees, small world networks, or scale-free, depending on the degree distribution. So there's a whole variety of them. And obviously they can be big or small. We can store them in different formats. So there are adjacency lists. People in high-performance computing mostly work on these compressed sparse row representations because they only work on structure. People like Aaron from the Graph Massivizer project, they work on graphs in kind of like maps because you want fast indexing, and a node is not actually just a number, but has some kind of like property by which you would like to identify that node and look it up very, very fast. And there's a whole bunch of graph formats, depending on what you actually would like to do with that. In Graph Massivizer, we try to support a couple of those, and some of them are extremely complex. When you look into GraphML, for example, it allows you to kind of to layer arbitrary data structures in nodes, and it's all in XML. So graphs can be extremely big and extremely complex in these formats, and specifications are like sometimes kind of like telephone book sizes, right? So I would like to introduce a little bit of a taxonomy for graph processing, but this is more from a graph massivizer standpoint, because this is actually what we promised in the project. So we want to do high-performance graph processing. We would like to learn graph representations, do that in a way traditional graph processing frameworks have done that, and all of that on top on knowledge graphs as well, right? So graph processing and high-performance computing is like more, we optimize a single algorithm kind of thing. I don't know if this is actually always true, but this is my experience with this type of people and these communities, right? So it's extremely difficult to make these graph algorithms fast because data is irregular. So memory access is kind of like not predictable. And there are people that use generations of PhD students to actually implement one algorithm fast on, let's say, one of these hardware accelerators. I had a master's student, Luke, together with Johannes Langhut, and we implemented BFS, which is breadth first search, like a graph traversal, on one of these AI accelerators, this graph core IPU, Intelligence Processing Unit, and it took half a year just to implement that algorithm. So it's extremely complex, and there is only algorithmic depth from my perspective. So people in these communities don't really think too much in abstractions. I mean, there are things like graph BLAS. Are you all familiar with that? So BLAS is practically a library for linear algebra, and graph BLAS is a graph pendant for that, and they tried to identify algorithmic building blocks in order to use them to assemble new algorithms, right? But this is not the standard, and especially not when it comes to implementing graph algorithms on these huge machines, right? A lot of that stuff is hand parallelized, so there is no framework, maybe MPI or something like that, but there's no actual programming model that allows you to parallelize, right? So you do everything by hand, and that's part of why it's so difficult to do. And they usually do that on GPUs, FPGAs, on special hardware, yes, like C, C++, and optimized assembly code, right? And very important, HPC people very often only work on structure, right? So their graph don't have attributes. It's a pure graph structure, and these are mostly edge lists that are like zero indexed because they fit into these data structures, right? So you have an array or an array list, and you can have fast lookups because you have an index. For graph processing and geometric learning, there are frameworks for that, and they are well developed. So there's PyTorch and this DGL and many, many more. I didn't look too deep into that. But these algorithms there are already prepared, and most people just use them. Obviously, there are people that develop the algorithms and develop the frameworks, but at least from my perspective, this is a very application-driven field. So a lot of people use graph neural networks, and it's not about getting more performance out of them, right? So when you go to these conferences, you see people with actual applications. And this also leads to this last point. So people in these communities actually think about the application of machine learning on graphs in a bigger picture. And this very often doesn't happen in these HPC communities, and which is all about getting more performance out of something without actual applications or one specific application. Graph processing in these more traditional frameworks, there's Apache Giraffe and GraphX, and these are mainly these big data frameworks. I mean, Apache Giraffe is a vertex-centric approach and only written for graph, but GraphX is the extension for Spark, for example, right? And these are all iterative algorithms then, in a kind of like bulk synchronous parallel fashion, because they inherit that behavior from the big data frameworks they are built on, right? Programming models are simple, and there are programming models that actually help you to parallelize, something like vertex-centric programming. Are you guys familiar with that? So it's practically describing a program from the viewpoint of a vertex, and the parallelization of that program is kind of like taken over by the runtime. So there are more of these programming models like edge-centric programming, and you have like super steps in which you evaluate and then come to the next step to work from the viewpoint of the next vertex again. But the parallelization is actually taken over by these frameworks. They mostly run on general purpose hardware, so they run somewhere in clouds, and people actually use them, right? So I have a friend working at Zalando, and they used to use Giraffe. I think that's what they did a couple of years ago, actually. People usually don't develop algorithms there, so they're like in machine learning with graphs, you have this collection of algorithms that are actually parallelizable, parameterizable. So you just put things in there and they run. And a very important graphs contain data, right? So there are actual labels in the vertices and in the edges. So vertex can be a user in the social networks with all its properties and things like that, right? And the last, and I don't know too much about that because before Graph Supervisor I have never worked with RDF graphs, but apparently I spoke to Aaron this morning. Semantic graphs are not optimized for algorithmic efficiency. So they are mostly stored in this kind of like triples, right? In which you have a vertex identifier, some kind of like edge identifier, and another vertex identifier. It's very often used in knowledge graphs. You have these triple stores. They're complex in the sense that you have all these different node and edge types and relationships. And Aaron said they are the opposite of deep learning because you always know what you do. So there's a clearly defined ontology, and each behavior is kind of like controlled. The ontology somehow makes sure that things are as they are supposed to, right? And people who use a lot of RDF use triple stores, often graph databases. So there's GraphDB, which we use in Graph Massivizer, RDFox, or like this Amazon Stardoc. Yes. Coming to more complex graph processing pipelines, and this is a little bit of an excursion in Graph Massivizer. So what we actually try to do there is we try to combine all of that and somehow develop a runtime that allows us to run graph processing in different graph processing steps, right, in which we plug algorithms together and parallelize them, plus execute them in heterogeneous environments, so something like compute continuum, things like that, on special hardware also. I work with GPUs. And we do that by defining graph algorithms, or by defining kind of like atomic computation units that can be an entire algorithm, but also a subroutine. Can be something like reading from a database or transforming one graph format into another, or executing a graph neural network, doing I/O, query database, all these type of things, right? And we have two different views of BGO, of these basic graph operations. So there's a descriptor, which is practically something like a function signature with an ID that somehow points to an implementation and some meta information. And we have the actual implementation that lives at runtime, right? So these descriptors, they live before, yeah. And the BGO is atomic computation. On a given graph, it has a unique signature and can have multiple implementations, for example, different algorithm, programming models, or target devices. A BGO is already available at compile time and is immutable. Oh, sorry, that was maybe a mistake. So a descriptor is a pointer to a set of actual graph, of actual implemented BGOs. And what we do with that, we assemble programs, and in Graph Massivizer, everything we get so far is static. So we don't do parallelization during runtime, at least not for now. There is the input of our execution environment is practically a data flow graph that consists out of these BGO descriptor types. And we enrich that, and this is partly during runtime and partly before, but I simplified and that we do everything before. We enrich that with information from micro benchmarks. So there's a component called the optimizer, in which we run each BGO implementation a couple of times in different hardware setups with different inputs, and learn from these from these experiments. And there's a component called the greenifier, which actually has knowledge about the environment and can make decisions based on energy costs or green energy, things like that. So what we're actually doing is we enrich this data flow pre-runtime, so that can all happen in your laptop. At least that's a simplified version of that. Look, later on, that might be a little bit more dynamic. And send it to the runtime, to an execution unit, which I call the master, but in the project is called the choreographer, in which a decision is made. So that's a classic distributed state machine, PetriNet kind of thing, in which we push token from one of these BGO descriptors to another. And when we reach one, we make a decision on which device we actually want to schedule. And there is a life cycle that's probably a little bit more complicated. Like I've drawn it here, but it practically rolls out a container with a subset of these BGOs. In this case, like this, read, partition, write kind of thing, and executes it on that device. We thought about designing the runtimes as follows. So there's one thing I forgot to say. We know all BGOs before runtime, right? So that's a huge difference compared to these big data frameworks. When you have something like Apache Spark, which is technically also a distributed runtime, you can generate code during runtime, right? So there is communication that is not just a signal to start, in our case, a BGO. I think in this big data framework, they call that user-defined functions. But there's actually code that is sent to the machines, right? And this is a whole other world, because suddenly you have consumers that are closures and have dependencies to code on other machines and all these type of things. So you run into a lot more complexity when doing it this way. And Graph Massivizer, we don't have that, right? So the entire program is kind of like, all these BGO implementations are there from the beginning on, and we can just roll them out in our distributed runtime. So this is one worker node, and there's one runtime component, which is practically like a process with a control layer and a data transfer layer. And there are signals from our master node, something like lifecycle, roll out this runtime, start the runtime component, and start each of these BGOs. Obviously, these lifecycles are a little bit more complex because there's debugging information. There might be information about errors and failures, but in general, that's the principle. Plus, there is something like a managed data transfer. So after each execution of the BGO, and this is not only true for one particular machine, but also in between physical execution units, we somehow need to coordinate and decide on how we actually exchange data in between BGOs. And that can be done with distributed file system, with graph databases, or even in memory with these off-heap zero-copy data structures. There's Apache Arrow, but I think there's also a couple of container-based approaches that allow you to share main memory in between Docker containers, for example, right? Are there any questions so far? Like, is that understandable? Okay. And there's one more concept we just discussed, and that's a graph handle. So somehow when we, I have it here also, when we start to execute these BGOs coordinated by the core graph or master node, we need a handle to not only the main graph, because we don't know, it's part of a file system, it's a query for a database. Is the graph mutable or immutable? There's a lot of meta information. There's information about statistical properties that probably influence the decision on which actual BGO implementation you want to take, something like degree distributions, average betweenness centralities, all these type of things. And there are subgraphs and sampled versions of this main graph that might allow us to kind of like shortcut this execution, right? So we have something like a handle, which we just discussing, to store in one of these RDF triple stores, because they're transactional. So you can just hand them from BGO to BGO and kind of like collect not only metadata in the main graph, but also information like immutability or subgraphs, samplings, intermediate results, all these kind of like things. So designing a distributed runtime in the way I've just presented, and that was very simplified, obviously, leaves a couple of questions. So what is an appropriate approach for accessing data? How to coordinate data transfer in a more organized manner? how to manage BGOs or even the life cycle of an entire program. And when we assume that this rich DAG is hand-assembled, how could we generate a programming interface or programming language, something like a compiler event that makes this BGO selection and maybe at one point even the parallelization transparent, right? So what we have said is the input of our runtime component, the master, is practically a description of the entire parallelized program enriched with information for micro benchmarks and the screenify information about electricity costs and things like that, right? But is there a way to actually program that? So what I would like to do now is to introduce a library I have written together with Tobias Herb, which is called Graphma, and this is for pipeline-oriented computation in general, but we have built a clone from it for graphs, right? And I hope that this is at least in theory capable of solving the challenges I have just presented. So Graphma is our approach for enabling transparent graph processing by organizing pipeline computations in a more structured manner. And this is obviously more. So we want to build graph processing pipelines, and it's only working locally so far. But in the context of the Graph Massivizer project, this is actually what we would like to achieve, right? So in a perfect world, it would be like this. So there's a simple program that counts the number of edges here, right, and parallelize that. This was a partitioner. We have the 3 edge counts here on a partition graph. So why not writing it like this? And everything somehow happens magically. So that's kind of like our goal. We followed a multi-layer protocol design. So we have something like a traversal layer that manages access and an iteration mechanism across different data sources. Directed data transfer that defines roles and rules for clear data movement between stages. And the stage is something like a BGO. There's a clearly defined operator model in which operators have life cycles. And there's the entire pipeline presentation. Right? So that's centralized the construct and execution of a pipeline. I will go through these layers now, and I think things should become a little bit clear. So first, the higher order traversal, and the purpose is to provide a unified approach to access and iterate through diverse data sources. Using the concept of internal iterators. Do you know what internal iterators are? Is it? No? Okay, something like a for loop is an external iterator because you can exit from the outside. But something like a for each loop that takes a lambda is an internal iterator. So you don't have control over the iterator from the outside. You just give it a lambda, tell it what to do, and it iterates over it, right? So that makes a lot of stuff transparent and hides complexity from the actual end user. So a traverser is an internal iterator that provides the ability to traverse a data source in a forward and so far in a forward direction, but we also have duplex iterators implemented now. So the idea is that there are different iterator protocols. So we have things like a try next, which is super heavy because after each iteration, you kind of like ask again whether it's possible to do the next one. There are for next loops that are aware of the size of the underlying data structure and therefore don't have this kind of like question, is there something new again? and while next, which is practically a for next, but has an iteration context in which you can hand over a kind of like termination criteria or some kind of like state to the next iteration. Our iterators have control that is practically the state of like where I am in iterating my data structure. And there's state, because this data structure can be an arbitrary thing, right? So that can be a network channel, that can be a map, an array, and yeah, so everything you can imagine and everything you can iterate linearly. Let's like see if I forgot anything. Okay. This is implemented so far, but there's absolutely no reason why this should not be possible, right? So what I try to, and I didn't have too much time with the slides, but what I try to depict here is traversal of a graph, something like a BFS. So I think it's entirely possible to hide these traversal protocols behind our traversal abstraction, right? And makes it transparent for the user then. So this is something we could think about in Graph Massivizer. And because this control is, or this state is actually modeled in a structured manner, this can a graph that lies somewhere in a graph database or even distributed, things like that, right? So it's all about implementing these traversals in order to access data. And the remaining stuff is transparent, right? That can also be a connection to a database, things like that. The second layer is the data transfer layer. So that manages the data flow between computational stages and components, and I wanted to delete that, but what we did is a pipeline segment or computation stage is split into these two parts. So there's always a port, a sender, and a receiver, or producer or consumer kind of like thing, right? Which allows us to distribute these pipelines also, right? Because access and this chaining can be synchronous or asynchronous, right? So I think it's very important to mention that because yeah, it allows us synchronous and asynchronous execution. Plus these segments have a life cycle, and I think that comes a little bit early because that's the implementation of a stage, but you can actually see that. So that's a computation stage that takes or calculates the radius of a graph, and this is the function that is called when the pipeline is activated, and this is the one that is called when the pipeline is closed, right? This is the one that is called on each value that flows through the pipeline. And I will come to that later. There are also stateful and intermediate operators. Let me just see if I forgot something. Okay, the obviously lifecycle managed. Yeah. We have a clearly defined operator model that serves as the core of pipeline construction and managing the lifecycle of operations to enable complex and stateful computations. And these are the three operators we actually offer, right? So there are transducers, which are intermediate operators, something you have seen before. It's kind of like stateless. And this could, for example, be something like a map is probably a good example for that, right? So making an integer to a string, things like that. They are materializer, also intermediate operators, that have a local state that you can actually access from the outside. Imagine something like a sort, for example, right? So that's not only a stateful operator, but also a pipeline stopper, because you have to kind of like accumulate the entire stream, everything that comes in order to sort it and to stream it into the remaining pipeline again, right? Important, we can exit that state from the outside and manipulate it. And there are terminal operators, and we have complete and partial terminal operators, right? So complete terminal operators process the entirety of the input data to produce comprehensive final result, something like a count, for example. And partial iterators are capable of producing output before, something like you want intermediate results of a stream, things like that. Yes. And finally, our pipeline representation. So this is how we assemble pipelines. So we have the traversal, it's an injector, there are our pipeline segments. These are actually pipes and ports. And we have something like a sink, like a terminal operation. Don't want to get too much into detail, but these pipelines, there is an evaluation strategy you can actually parameterize these pipelines with. You can decide whether you want to have lazy or strict evaluations, right? And they're usually lazy. So what happened when you push the evaluate button is practically that you do a function composition. So you run contravariants through your pipeline and you squeeze that together into one kind of like function call. And this thing has a life cycle, right? So we can actually evaluate the entire pipeline and do optimizations. I don't know, kick out certain operators when they when they're not needed, or optimize with different implementations, right? So each of these pipeline segments here can just be a descriptor for what type of computation we would like to take. And while hitting this evaluate, like for the lazy execution, we actually decide for concrete implementation. I think that's important to mention here, right? So yes, there's this. I thought there's one slide. Yeah, that was the example I wanted to show before. So this is actually what I've shown already. Sorry, I wanted to delete that in the previous slide, but that's one of these operators again, right? And that's the contravariant composition of our pipelines, right? With this actual life cycle in which we evaluate them. This is an example that doesn't use graphs with our front-end API, and I think it's very clear to understand, right? So we have a data source, and let me see if I have a version that's a bit more. Yeah. So we have a data source, and we call a sequence on this data source. This is how we actually call this container. We drop two of the elements in there. We filter out the ones that are not equals E. We do a sort. We append a list of new characters, and then we print them. And this is kind of like terminal operator that counts, right? Important because the evaluation of a pipeline is kind of like lazy and has a life cycle. This terminal operator can actually choose the iterator protocol, right? So when this is match B or something like that, right, we can use a while next loop with the criteria. When we reach the E the first time, we kind of like stop, right? Yeah, I I think that's important to mention. This is the same example in our non-front-end API, so to speak. So what we're actually doing is we build this data source here, and this returns us a traverser that has learned to traverse this array, right? Or this knows how to traverse this array in both directions. This is contravariant, so this is actually written the wrong way around, right? So we apply this data set, we do the drops, which are both stateless pipeline stages and this kind of like intermediate operators that don't have a state. There is the sort, which collects everything that gets streamed into this operator and sorts at once and starts streaming it again. And then we have the append and the peak. Important, only this evaluate triggers the evaluation at the end, right? Everything else is practically function composition. I think that's all I wanted to say. So the idea is, like, why can't we do that with graphs also, right? So this is an example from what we have built so far in Graphma. And it's, to this point in time, not more than being able to read these graph formats with dedicated traversals and have a couple of graph processing operators that do not counting or something like that, but calculate between centrality. And the main idea is to have something like a graph interface that makes the underlying format actually transparent, right? So this traverser is already chosen based on the appropriate graph format the pipeline is supposed to work on. And this is only an interface, right? So you can hide all that complexity from the user when you do it the right way. And this actually is a message I would like to transmit. Yes, there's a filter stage that takes out, sorry, this is what I forgot to say. This is a database of a lot of subgraphs that get streamed from the beginning to the end, and we just count the clusters, I guess. Oh no, yeah, we count the clusters that have a betweenness or average betweenness centrality from like less than 0.5. You all know what betweenness centrality is. It's just okay. Yeah, we filter out those that are loopless, so to speak. We calculate the betweenness centrality and filter out those subgraphs that have a betweenness centrality above 0.5%, 0.5, sorry. Yeah, main idea, this is an interface and makes the graph format or even the underlying representation transparent. And these are just interfaces to implementations for BGOs, right? Practically what the BGO descriptor is at the end of the day. And while evaluating this pipeline, we choose the actual implementation. Yes, and I think that's it. That was 45 minutes. I did that work together with TEWI, who has contributed a lot, or like mainly wrote the underlying pipelining framework, and Brian, who was also working at Cintiq on the Graph Massivizer project. And what I've done is built this graph layer on top, actually. So that was my presentation.
Thank you, Daniel.
I hope it was understandable.
Definitely.
Okay.
So I have to say it's a real pleasure to work with him in the project. Through his formal thinking, he brings a lot of clarity to everything we do there. And it's a lot of help to work with him, and it's great to have you here. So now let's open the floor for questions. Evan.
Thank you. Thank you, Daniel, for the interesting talk, the abstractions. I have a question on abstractions. abstractions usually come with performance loss as well. What is your experience developing GraphMa here or the library? Do you lose performance versus handwritten code? Is there noticeable cost?
Okay, what I've done so far is these operators here. I think we had an example of a very simple one, right? So this is only a Java graph processing library called jgraph-trupt. But what you can imagine is this is a call to actually code that is performant, right? And then it's all about data transfer. So when you don't have mem copies in between these operators and use something like zero copy of heap buffers, supposedly I hope they are fast, right? And your algorithm adapts to that and doesn't have a lot of copies, right? This can be a super fast C implementation or an implementation of some accelerator code, right? It's only hiding that behind this kind of like facade of a pipeline stage, right? And that can even be more, right? So that can be code, like this open here, that evaluates what's in the pipeline at runtime when you hit the evaluate, right? And makes a decision for which implementation you would like to choose, right? So this is the way we have constructed our pipelines. So this open here is only called when you actually assemble your pipeline at the very end. I think I had an example here, right? So this evaluate here and can choose an implementation that is native code. So I have experience. It's super slow because I use this Java library, but the idea is to make that transparent into actual fast implementations. Yeah.
And the second question, when you introduced BGOs, you said these are atomic compute units, right? Yeah. But the examples on the left side of the slides showed quite complex operators, like betweenness, computations, partitioning, clustering. What is the precise definition of atomic here?
So this is, I can only say this is what we wrote in the deliverable, and I'm also not too happy with that, because I think something like atomic building block for graph processing would be a traversal, for example, right? A lot of algorithms work on, I don't know, when you have influence counting or something like that, that works on a lot of breadth first search traversals, right? So this is defined as it is there, but in practice that can be a complex algorithm. So I think the idea in the Graph Massifizer project is to use what's already there and not to re-implement algorithms based on the building blocks we have built.
But the basic idea is to have this as an indivisible operator.
Is that, sorry?
Indivisible, non-dividable, yeah? Like a transaction, okay. It happens completely or it does not happen.
Okay, in a perfect world, right, where we would have enough resources to actually determine these basic building blocks for graphs, right? And Graph Blast, they have tried something like this, right? And they work on that for decades. We would re-implement all of those, right? Have actual BGO implementation for each of these hardware accelerators, GPUs or IPUs, and the different graph properties, right? But have actual atomic building blocks, right? And when you would have something like this, and you do something like evaluate your pipeline at the end of the day, you could do real optimization based on atomic building blocks, right? And you could kick out a lot of stuff. When I have something like, I can't come up with an example right now, but there's something like influence counting, which is running a lot of BFS on a graph. And the second step in the pipeline is an algorithm that also uses a lot of BFS. There's no reason to do that twice, right? So it's just executing this BFS once, right? So you could really optimize on this level. But for very clear reasons, it's not possible, right? So like our EU project doesn't have 2,000 people, and we can't re-implement all the graph algorithms that are out there. But you see the idea, right? So I have used the BGO stuff because it's graph massifier things, but these are basic units of computations in general, right? So like in this example over here, oh wait, this one, that could be something like a filter, drop, sort, like any kind of other operations that works on any kind of data, right?
Reza.
Many thanks, Daniel, for the interesting talk, comprehensive one. I would like to ask a challenging question. Since in the choreographer as a backend tool, we are always thinking about DAG processing or workflow processing. How do you see the future for just hypergraph, representation processing or other types of, graph representation processing? At the moment, we only have DAG, but if we want to have hypergraph modeling or processing, which type of challenges or insight?
So you mean that the program is actually a hypergraph, or that we work on hypergraphs?
Imagine we have the application, the component of the application connected in the hypergraph representation. Also, we have infrastructure in the hypergraph modeling. So we just want to bind or match the application into the infrastructure. In this time, we have hypergraph.
I don't have too much. I have never seen it, and I don't have too much experience. So, but I didn't build too many distributed runtimes only during my master. So, like we had something similar to that. There was a project called Aura, which became, which was also with Toby, the guy I've presented, and we have built exactly that, right? And there was like a PetriNet-like approach, in which we had different names for that, right? So what we have here would be a logical execution plan, and as soon as we assign a hardware resource to that, it would become a physical execution plan, and then we had a PetriNet kind of like thing which visited these nodes, and then there was a more complex protocol that speaks to the actual physical execution units and the deployed runtime component in there, but I've never used hypergraph to present a program. For me, these were always data flow graphs. Like what we did and what we don't do in Graph Massifier, we actually model control flow over that data flow, right? So in Graph Massifier program always looks like this. There's no branches and there's no looping, right? So you can imagine we would like to do this 400 times in a row, right? So we actually modeled data flow in control flow operators. So there was something like a for loop, for example. Yeah.
But from my side, I still kind of understand that at what level you are composing the graph operations, but how would you connect to Reza? So Reza, as far as I see, you are kind of a more functional, high-order specification of basic graph operation composition, while Reza is more for the high-performance coordination at an imperative level. No? So do we see any kind of translation between the GraphMa, your tool, and Reza's tool? I don't know. It's not. So it's complementary, but not really. It's different. Abstractions.
It's different because this goes beyond what we promised in Graph Massifier, and this is because we didn't promise optimization or automatic parallelization and things like that, right? So like with GraphMa, we really have a, it's called functional way of describing pipelines that is clearly structured and makes code composable and allows us to do these optimizations, right? But what you could do, for example, is like something here, right? GraphMa could be the component that actually, sorry, it's maybe one slide later, so it's maybe even better. could be the component that controls the execution of BGOs on an individual device, right? And this is also not very clear in Graph Massivizer. Do we always deploy one extra container, or do we deploy sequences of BGOs on a machine? And I would say a sequence makes sense. But this layer here could be Graphma, right? So it depends on how strong we would like to make, or how smart we would like to make our runtime component. So we could assume that Reza just transfers the information that 3 BGOs are supposed to be executed in a row, and we can compose that with Graphma. That would be possible. Or Reza just tells us to execute 1 BGO. When we tell him that it's executed, he would start the new one. I think it depends on how smart you want to make your runtime and how much you would like to optimize there, right? I like this idea of a traversal. So when we assume that, and this is very Graph Massivizer specific right now, but I haven't seen a BGO that is only a transformation or something like that. For me, it's always a kind of like read, execute an algorithm, write kind of combination, right? In which we access a database, a distributed file system, and execute an algorithm to write a result back somehow. I forgot what I wanted to say. Yeah, I could assume that like we in the Inceptor built this in Graphma just to have a clearly defined pipeline, but from Reza's level, it would be more something like we describe a program. Oh, I had a slide here, right? Like this would be the ideal situation. Right? We describe a program very simple as a sequence of BGOs, and everything is done.
I see it as, as a formal specification from your side and imperative coordination from his side. And, I think there were lots of works even in the functional programming community, how to map these two worlds of functional specification, where variables data is of no use, it's just function. And then you have to coordinate it, and there is really about high performance, parallelism, all these things you don't want to care at the functional level.
And that's really the idea, right? So you just compose symbolically, so to speak, and like everything that is happening
But that would be a project on its own. Maybe the follow-up. Maybe the follow-up. We have an idea now.
Obviously.
So next question. Let's move on. Farzad, one question.
Thank you for your nice presentation. In the beginning of your talk, you mentioned that for implementing BFS algorithm, Graph Massivizer, traversal algorithm, you and your master students work on this.
That was before.
Yeah. And what's the complexity did you tackle with that? Because I'm curious about those complexity that is about the algorithm, or just managing the data between the, for example, pushing the database and retrieving for doing more processes?
So that was before Graph Massivizer and like during my PhD, I guess. And Luke Burkhardt, he was and Johannes Langhut, who was my PhD supervisor at the time, master student. And we developed that as a part of, I think in the beginning I showed one of these large graphs, right? So we built a system in which we collected millions and millions of Twitter accounts and built this detection network. And the idea was, could we do influence counting very, very fast, right? And the basic building block for influence counting was BFS. And we had this new hardware accelerators that was back then at Simula. So he started working on benchmarking BFS. And the thing is, obviously, you have like a new hardware. I think the IPU has a programming model that is relatively easy to understand. So they have BFS, so there's always it's bugs and cross parallel, BSP. So there's always an execution phase that is followed by a communication phase, and then you have an execution phase again. So the whole execution is determined pre-runtime, so to speak. So this whole data flow graph is practically compiled for you and is known pre-runtime, so it takes time actually, right? And yeah, you just described data transfer and practically the lambda you schedule on this execution. But what you can imagine, it feels like a huge cluster you program against, right? And obviously there's a whole specification you have to read. I think not for the BFS case, but they later worked on these genome sequencing algorithms. They did optimizations in assembly, right? So you have to really know what you're doing. I think there was yeah.
Thank you.
It just takes a while, right? So.
Ale?
Thank you for the presentation. I have a question about the first stage of the pipeline, traversal stage. It's not the traversal layer, which the first layer of the pipeline. As far as I understood, it's not necessarily traversal over the edges. I didn't understand how is it like. It can be different graphs or something like this.
It can in fact be everything you want it to be. Let me just see if I can show one. I don't find my mouse, sorry. Here it is. I think we had one and the test scenarios, right? There was a stage. Sorry, I can't find traversal implementations right now. I know, sorry. One second, I think I will have it soon. So this is a graph traversal, right? And this is the traversal that traverse one of these graph formats, GraphML. And what it's doing, it's pushing edge by edge, or it's not actually pushing. It was very hard for me to describe that in the presentation. So like what we really do is like when you push evaluate on that pipeline, right? We practically compose a whole bunch of functions, the ones you have composed there, right? You have described the composers, and we push it into this iterator, right? So like there's an onNext function, or like there are these three protocols, right? TryNext, forNext, and whileNext. And whileNext has this context which we give from iteration to iteration, right? And the whole loop is actually happening here. And what you hand in is just the action, and this is the consumer. This is which is actually the composed pipeline, right? So the traverser is at the end of the day also the execution context, right? So everything becomes transparent and everything happens internally in this traverser, right? And you can implement them as you want, right? So I have one here that actually, and I know we're running out of time, but that iterates over the suit sparse collection. So this is a whole bunch of graphs high performance people use for, or actually sparse matrices, high performance people use for benchmarking. So there's a traverser that iterates over each of these graphs, but I have also one that iterates on an edge level, right? So it's your decision. It's the way you implement it.
Okay. Yeah, thank you.
The last chance for questions. Thank you very much, Daniel. Very interesting talk, and yeah, we are happy to continue collaborating.
Thank you very much.